In the back of these steam tables exists this big chart that you'll fold out. Very, very helpful, especially once you learn how to use it. So this is your Moyer diagram. On the left-hand side, starting up here, and then coming down in this direction, as well as on the pure right-hand side, this is enthalpy, specific enthalpy in BTUs per pound mass. So those are the lines going straight across. Now, I'm going to draw this in a minute, but this big, thick black line represents our saturated vapor line. The Moyer diagram that we have right here does not concern itself with anything other than the wet vapor, the vapor dome here, and this is all to the right of the critical point, this big, thick black line. For instance, you'll see atmospheric pressure, and it's very key to note that the pressure lines are diagonally from the lower left to the upper right. So here on the atmospheric pressure line, I could come up here and intersect the saturated vapor line, and so I could see what enthalpy is once it became a saturated vapor. And I see about 1,150 BTUs per pound mass once water is a saturated vapor. I could look that up in the steam tables and verify it. So I go to the saturation temperature and pressure for water at atmospheric, and I know that it's 212 degrees, so I'm going to go right here. And then I'm going to go over to the enthalpy, and hey, looky there. H sub G at atmospheric is 1,150 BTUs per pound mass, 1150.3. So I know that if I'm on this black line, that I'm a saturated vapor. Anything underneath this line is once again going to start introducing moisture, and quality will be less than 100%. Now this has not quality lines, it has moisture content lines, and you'll see them right here. So as you start getting deeper and deeper into the vapor dome, you'll see you start out at 1% moisture content, and you start going all the way down this way, and now I'm at 30% moisture content, which means I'm at 70% quality. And you see it goes all the way down and ends at 56% moisture content or 44% quality. So I could intersect. If I existed right here, if I knew the state existed right here, well, I'm at atmospheric pressure. I'm on the saturation line of atmospheric pressure. I can look up that temperature, 212 degrees. But look at these lines, these weird lines. The moisture content line swoops up and then it swoops down. And I'm actually existing at 14% moisture content. If I wanted to know what the enthalpy is at that point, I come straight across and I see that it's about 1,015 BTUs per pound mass. If I was to do something at a constant pressure to raise the enthalpy, like in a moisture separator reheater or a moisture separator, look, I come up to here and I stop right there. I've reduced the moisture to 2% moisture content and increased the enthalpy to 1,130 BTUs per pound mass. If I want to know what the corresponding saturation temperature is to any one of these diagonal pressures, over here on the right, these are all corresponding saturation temperatures. So here's the 200 degree line coming on in, and it stops just below atmosphere. Well, we know it should. There's not a 212 degree line. If I wanted to know what the saturation pressure is for 540 degrees, well, we knew 544 was 1,000 psia. So if I follow this 540 degree line to my saturated vapor line, I should intersect 1,000 psia. So let's do that. Follow it, follow it, follow it. Up, there's 900. And we're right around 900 because 1,000 is just a smidgen to the right. And we know it's 544, so this intersects somewhere around a little bit past 900 psia. If I wanted to know the enthalpy of 100% quality steam at 1,000 psia, right here is the 900-pound pressure line. You'll see that each one past it is 100 pounds. So that is the enthalpy This represents the enthalpy of saturated vapor at 1,000 psia. And I see it's 1,100 and about 92 or 3 BTUs per pound mass. And if I was to come over here, I want to know that temperature, see what temperature intersects it. Well, I just come over here and I see and follow it up, and I see that it's just a little bit above the 544. So these are temperatures. If for some reason I was to lower pressure this way straight across, and I end up here at a new lower pressure but higher temperature, this region all up here represents superheat. You can kind of turn this way, and it was over to the right on our TS diagram. Well, this is the superheat region. The other thing, so we know we have pressure lines going diagonally. Key part, we're going to have to recognize that we can drop pressure this way then, or I can drop pressure this way. We're going to give you a learning tool. Moisture content exists down here in the vapor dome. Actual temperatures occur here. And let's say I was at that 600 degrees, 1,000 psia we did previously when we found we had superheated steam exiting our fuel bundle. Well, and we recognize it as 56 degrees superheated, but I was at 600 degrees. So I'm going to come up here, and here's the 600 degree line. And now what I'm going to do is I'm going to intersect the 600 degree line with 1,000 pounds. So here's the 900 pound pressure line, and I'm going to take 600 degrees and intersect it. And they're kind of weird. See, they swoop down and to the left towards their pressures. So I got to stay right in the middle between 580 and 620, and then intersect the 900 pound pressure line, and then find the 1,000 pound pressure line. Now I can see the enthalpy right there. I can go over here and see that it's about 1,260 BTUs per pound mass if I existed up there with superheat. Then these other lines exist. These lines, right, as numbers exist. These are the degrees of superheat. And we know that I had about 56 or so degrees of superheat, and that's what these are, degrees of superheat. These numbers right here. So if I'm at 600, well, I don't have it anymore. If I was at 600 degrees, 1,000 pounds, we already knew that was 56 degrees of superheat. I should have intersected somewhere. You got to follow these swoop up and down, very weird too. So I should have been just below this 60 degree superheat line. So it's very useful. We're going to be using this a lot when it comes to solving exam questions and solving ideal turbine work and throttling processes. Yeah, you'll really like this when we get to know it. It's not that hard. We'll have a ruler going this way, top to bottom, dropping pressure, and you can see that I'm lowering the enthalpy. So this will be a turbine dropping pressure this way. If it's a constant enthalpy process, we're going to find out that I dropped pressure through an open safety relief valve, that's a constant enthalpy process, and the outlet of it, of the SRV down at in the torus or in your suppression pool, is going to be superheated steam. And we can figure out what the temperature of that superheated steam is supposed to be. And you'll see that it's going to be much less than expected sometimes. You're going to go, oh, I'm at 544 degrees, and I'm going to open it up. The SRV, I should be at 544 degrees, but in fact, you're not. It's only at 320 degrees, and you may think, oh my heavens, it's just simmering. Well, that would be the same mistake that 3 Mile Island made. And we're not going to make that mistake. We're going to understand how to use this Mollier diagram bulletproof so that doesn't ever happen again.